If your data has dates, a normal split can secretly make your model see the future. This video shows the safe split pattern you should use instead. You have probably trained a model and watched validation scores that look unrealistically good. That usually means the training data leaked information from the future. By the end of this video, you will know how to split time series data, so your validation honestly reflects future performance. You will also see a simple baseline pipeline that shows the difference between leakage and a safe split. I'm Professor Pi, teaching AI foundations with simple Python. Time series problems are everywhere. Want to forecast demand, detect fraud, or predict a sensor reading over time? Success is a model that works on future data it has never seen. The usual random shuffle that is fine for IID data breaks badly when order matters. Models can pick up subtle signals that only exist because later rows leaked into earlier ones. The intuitive idea is simple. Train only on the past. Test only on the future. Build features that summarize recent history, like lagged values, and then cut the data set along time, not by random rows. The strength of this approach is honesty. The downside is less training data and the need to think about non-stationary behavior when regimes change. We will build a tiny example. First, we will synthesize a small trending time series and create lagged features. Then, we will show what happens if you shuffle and split randomly. Next, we will cut the data chronologically to stop leakage. Then, we will use scikit-learn TimeSeriesSplit for rolling validation. Finally, we will train a simple scikit-learn linear regression on the past and measure performance on the future, so the steps feel concrete and comparable. Now, we create the toy data and features. This snippet builds a tiny, noisy trending time series and aligned lagged pairs. It starts by generating a short sequence that trends upward with random noise added so it looks like a realistic signal. The code then creates one or more lag features by shifting the series so each row contains recent past values alongside the current target. The top of the snippet shows how the series and the lagged columns align by dropping rows with missing lags. The main idea is to produce a table of samples, where every row represents a time point. The predictors are recent history, and the label is the next observed value. Next, we demonstrate what a random split can do. This snippet simulates a random shuffle split to reveal future leakage risk clearly. It takes the lag table and randomly shuffles rows before splitting into train and test sets, just like typical IID workflows. The snippet then fits a quick baseline model and reports validation behavior that looks optimistic, because shuffled training rows may contain information derived from later time points. The point shown is qualitative. When you shuffle, the model can effectively learn patterns that span the original timeline, producing inflated scores. If you change the test fraction, you simply change how much leakage ends up in each partition, but the leakage mechanism still exists. Now we enforce time order with a simple chronological cut. This snippet creates a strict chronological split that prevents future leakage. It slices the lagged table by index or timestamp and assigns the earliest portion to training and the later portion to testing. The core lines choose a cutoff point in time and split rows based on that cutoff, rather than random sampling. That ensures no row in the training set has information that originates later in the series. A key knob here is the cutoff location. Moving it earlier gives more future data for testing and less history for training, while moving it later gives a bigger training window at the expense of a smaller holdout. Next, we use a proper time-aware cross-validator. This snippet uses scikit-learn TimeSeriesSplit to score a model without leakage. Time series split, which creates multiple sequential train and test folds that respect time order, is applied to the lagged dataset. So you get several increasing training windows and corresponding future test windows. The snippet demonstrates how to iterate folds, fit a model on the first fold, then expand the training window and score again on the next fold. The important parameter is the number of splits. Increasing splits gives more validation folds, but makes each test window smaller. This provides a stability check across time and highlights performance trends as you move forward. Finally, we train a simple baseline and evaluate honestly. This snippet trains scikit-learn linear regression on the past and evaluates the future. Linear regression, a simple model that fits a straight relationship between features and target, is trained on the chronological training slice or the rolling training folds. The snippet computes a metric, like mean squared error, which measures the average squared difference between predicted and actual values to quantify performance on the holdout. The code shows that scores from the non-leaky chronological split, or time series split, are usually worse than the shuffled split, but they reflect real generalization. This confirms that honest splitting gives a realistic estimate you can trust. Mapping this toy into a real project is straightforward. Replace the synthetic series with your real-time index and create domain-specific lags or rolling aggregates. Use the chronological split when you need a single final holdout, and use time series split when you want to validate across multiple periods. Recap. What it is: a time-aware train test split that keeps the past separate from the future. When to use it: always for forecasting, anomaly detection, or any model where the input order matters. One caveat: you may need more data or domain adjustments because honest splits often reduce training volume and reveal non-stationary behavior. Next step: tune the lag window length in the pipeline to see how much recent history your model actually needs, and track performance as you change that parameter. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.